what we're starting today is polynomial functions. Polynomial functions. And we've actually been talking about a polynomial function already. We've been talking about some of these already. Because if you look at this here, this chart that's given to us, when the degree is 2, we're talking about a what? A quadratic. That was the entire last chapter, wasn't it? The entire last chapter was over quadratics. So we have been talking about quadratic functions. We've been talking about, well, quadratic functions. We've been talking about a type of polynomial function. Now, there's some others. There's one that's called a constant. And when we talk about constants, we're just talking about a number. Y equals -14. We're talking about our horizontal straight line. Linear functions, you talked about that especially a lot in Algebra 1. 5x minus 7, y equals mx plus b. That is a linear function. It is a polynomial function. Then we talked about quadratics. Now what we're going to start delving into is cubics and quartics. These are these higher degree polynomial functions, where the biggest exponent is going to be greater than 2. Because up until this point, you've never dealt with a function that had a bigger exponent than 2. And that's what we're going to be looking at this year and in this chapter. And it can go higher than 4. We can go up to 12, 13, 14, 15. We can deal with any higher degree polynomial function. And this here looks terrible for most of y'all. This here is just a way to define any higher degree polynomial function. Any higher degree polynomial function. And what we're doing today is actually not as bad as what you might think. So the first thing we're going to do is go over some vocabulary and kind of ways we write this. Standard form. Writing the polynomial in the order of descending degree from highest to lowest power. So when we look at any of these functions, if it's going to be in standard form, the biggest exponent, the variable with the biggest exponent always goes first. It always goes first. And in alphabetical order. So if we're dealing with x, with everything with just in terms of x, like we've seen already with our quadratics and other functions, x is going to go first. The biggest exponent with x would go first. If we had more than one, whichever one was in alphabetical order, x, y, z, that's why we always put y first, because it's alphabetically, it comes first. So if we have x and y, normally we would write y first. But there's some different properties, because sometimes it's not always that case. Because normally if we're dealing with just x and y, x goes first. It's just the properties of it. But when we talk about writing letters together, they go in alphabetical order, y then x, or x, y, sorry. X is before y. I don't know what I'm talking about. I'm not an English teacher. X would go first, then y. If we talk to say A would go before x, or B before x. So we normally keep it in alphabetical order, and then we rank the powers from highest to lowest. Leading coefficient, this is something that's going to come up from here on out. And especially with pre-calculus or other things that we talk about leading coefficient. The leading coefficient is the number in front of the term with the highest power. So whatever number's in front of it is the leading coefficient. And the leading coefficient can be 1. We can have a leading coefficient of 1 or -1. Those work. But we can never have a leading coefficient of 0. It just doesn't work. A leading coefficient can never be 0. A leading coefficient can never be 0. So a leading coefficient can be any other number except for 0. So those are kind of two key terms. Now what we're going to look at next here, and again, we're just getting into kind of semantics and kind of what it is and what it's not. Now what we're going to be looking at here is kind of defining what is a polynomial function. Is it a polynomial function? And we could go through the details of explaining all the intricacies of what a polynomial function is. But instead of doing that, I find it easier to define what it is not. It is not going to be a polynomial function if the exponents are negative. If we have a negative exponent, it is not going to be a polynomial function. So when we're looking at polynomial functions, we're looking at a function. If it has negative exponents, it is not a polynomial function. The next one. The exponents can't be fractions. If it's going to be a polynomial function, we cannot have fractional exponents. It will not be a polynomial function. Do you remember what it would be? If we have fractional exponents, it's not a polynomial, it's... Well, it starts with an R, right? It's a rational or a radical. It's our radical functions. I would just be writing these here. Variables aren't inside a radical. Because these here, this is really helping us define what a polynomial function is. Because a lot of the times it's harder to be able to say, is this a rational function? Or not rational, polynomial function? Because we can go and list all the properties that they do have. But it's easier to look and see what shouldn't they have. Because if they qualify for one of these here, it's easier to pick them out. We have two more. Variables aren't multiplied together. And lastly, variables cannot be in the bottom of the fraction. So I'll give you some examples here because exponents aren't negative. We can't have x to the negative 2. That's not going to work. Exponents aren't fractions. So x to the 1/2 won't work because we have a fractional exponent. If we have fractional exponents, it's not going to be a polynomial function. Variables are not inside the radical. I can't have the square root of x. Variables aren't multiplied together. I can't have xy. And variables cannot be in the bottom of a fraction. So these here are all examples of what this means. So kind of what this is telling us is if one of these show up, or more than one of these show up, it is not a polynomial function. It's not going to be a polynomial function. If it has any of these here, negative exponents, fractional exponents, variable inside of a radical, variables multiplied together, x times y. X times x is fine, that's just x squared. But two different variables can't be multiplied together. And variables cannot be in the bottom of a fraction. It just won't work. So if we get any of these here, if any of these here show up, it is not a polynomial function. And if it is, we're going to write it in standard form. Any questions on any of this here? And the degree is the biggest exponent. Because we saw that a little bit earlier where it talked about in the table where the degree and the biggest exponent line up. Any questions on any of this here? We good with this here so far? Decide whether each function is a polynomial function. If so, write it in standard form. State its degree, type, and leading coefficient. So that's part of why we have the table. So let's work through this here. Let's work through the first one. A, f of x equals negative 2x cubed plus 5x plus 8. Is this a polynomial function? Yes. We don't have any negatives in the exponent. We don't have any fractional exponents. We don't have a variable inside of the radical. We don't have two variables being multiplied together. And we don't have a variable in the bottom of a fraction. Yes? So decide, yes, it is. Yes, this is a polynomial function. If so, write it in standard form. Is this in standard form? The biggest exponent is 3, yes? We don't have one squared, but then the next one is just x, and then we have a number by itself. So yes, it's in standard form already. We don't have to do anything. The degree. What would the degree be? The degree is the 3. The degree is the biggest exponent. And what is the biggest exponent here? So the degree for this would be 3. Now, I abbreviate leading coefficient as LC, leading coefficient, partly because I don't have space to write it on the board. Now, the leading coefficient is what? The -2. It's the number in front of the variable with the biggest exponent. And the number in front of the x cubed is -2. So did we answer every single part of this question? The type. So the degree is 3, yes? Now, every one that has a degree 3 is going to be a cubic. Degree 3 is a cubic. Now, I did give you that chart already, yes? So, degree 2 is quadratics. We talked about those last chapter, so hopefully those will be easier to remember. Degree 3 is cubics. Degree 4 is quartics, if I'm remembering this correct. It should be. And degree 5 is quintics. Yes? Yes. It doesn't go up to 5, but it would be quintics. Because quin, Q-U-I-N, quintics is 5. Okay, let's look at the next one. Letter B. Is this a polynomial function?
We need Reagan Havard and Tori Dougherty.
Yes. Exactly. Because this here, this radical stops, because it'd be tempting to say that it's not. But if we look at this radical, it stops before x to the 4th. It stops before x to the 4th. So it might be tempting to say, but because it's not under the radical, this will be 1. This will be a polynomial function. This is yes. Now, if that extended over to x to the 4th, then no. So this is yes. Now, is it written in standard form? No, it would be g of x equals what? X cubed minus 12, because we need to go 4, 3. There's not 1 squared, there's not 1 to the first, and then we have our number. So the powers are now in descending order, yes? Okay, so we got that. What is the degree? What is its type? Quartic. Did I call it quintic? 5 was quintic. Okay, good. Making sure. And leading coefficient? Radical 2. That's it. Questions on this here so far? Well, no, it's not just this easy. How about C? No. We're done. Yeah. Because what did it say? Decide whether each function is a polynomial function. If it is, then write all this stuff. No, this is not 1. Because why? Because x is to the negative first power. X is to the negative first power. So this is no. This would not be 1. Okay, let's move on to the next one. How about letter D? No, why not? We have a variable in the exponent. This here would technically be considered, or is not technically, it is an exponential function. It is an exponential function. Any questions on these here? We good to move on to the next page? Good? Okay. Let's look at the first two. So number one, is it a polynomial function? Is it written in standard form? What does it need to be? Negative 1.6 x squared. The degree. Type. Quadratic. Leading coefficient. And that's it. Questions on this here? How about number two? Because we have a negative exponent. So that automatically makes it no. Any questions on this here? All right. Let's move on to the next thing. We only have two things left that we're going to cover today, and this is the next one. Okay. So let's look at this one here. Okay. I'm going to cue this up. So evaluate f of x equals 2x to the fourth minus 8x squared plus 5x minus 7 when x is equal to 3. What are we doing? We're plugging in 3 for every value of x. So the way we'd really write this is f of 3. I replaced x with 3, yes? So everywhere there's an x over here, I'm going to replace it with 3. Now what can we do? You can plug all this into the calculator, can't you? Yep. Or if we did this by hand, 3 to the fourth is going to be 81. 3 squared is 9. 3 times 5 is 15. 9 is 7. 2 times 81 is 162. 72. 15 minus 7 is 8. And I believe this should be 98. I want you all to double check that one. Make sure I did this one right. Okay, so y'all get 98? And that's it. That's all I have to do for this here. Questions on this here? We good with this here? Okay, let's move on to the next one here. Okay. Let me grab so you have it here on your note sheets. I'm going to show you something fancy we can do with this graphing calculator. Now, up to this point, we've told you time and time and time again, do not use variables in the calculator to calculate things or to try to factor. So, and this is kind of what I'm about to show you is the reason why. Now, what value of x are we plugging in for this example? We're plugging in the value of 4 for x, yes? So on that graphing calculator, if you have it, do 4. Here. Yep. So you're going to type 4 STO, S-T-O, x, and hit enter. And what you've just done is you've just defined the value of x as 4. So any other time you plug x into the calculator, not for graphing. Graphing's different. It understands that it's not going to be just 4. But anywhere I plug in here, the value of x, it's going to think it is plugged in as what?
4.
4. Okay, now what I can do is go negative 2x to the 4th. Cursor over, plus 6x to the 3rd. Minus 3x plus 11. And hit enter. And it tells us what? That it's negative 129. Now at this point here, it's like, well, that's not any faster than just plugging 4 in, right? I mean, it's about the same, isn't it? Because a little less buttons, so on and so forth. But what happens if it told us to find not just the value of 4 for this function? It also told us to find the value of negative 2/3. Well, what can I do? I can do alpha y equals enter negative 2 over, not negative 3, 2 over 3. So x enter. So it just redefined x as negative 2/3, yes? Now, probably the next thing we would do, or you'd be tempted to do, is go negative 2x to the 4th, type that whole thing back in. Watch this. If I cursor back up and hit enter, did it just bring it all back down? I didn't have to retype it. Now, if I hit enter, is it going to give me negative 129? Because since we redefined the value of x, it plugged in the new value. So I could do negative 2/3. Well, now it wants 8. So x enter. And I just done I did it for 2 different values faster than I did one of the doing it by hand, didn't I? Just another one. This here is nice. This here makes these nice. It makes them easy, especially when we start getting to later on in the chapter. We start talking about a theorem called the rational zeros theorem. And the rational zeros will give you all the possible rational zeros of a function. Okay? And being able to do this is going to make your life 7 times easier. Actually, I might even be underestimating that. The pre-calculus class, use that theorem to find all the possible zeros, and we can plug them in. And we'll get into that, and it'll help us figure out which ones would work and which ones don't. I think we spent a half hour finding all the possible rational zeros for some of these functions. We won't get to one in that depth or that detail because of, and it'll make more sense when we hit there. But this here, if I'm given multiple values to plug in, heck, I could do 10 values in under a minute, couldn't I? Because once I get it set up, it's just doom, doom, changing that value, plugging it in. And you can blow through these. Any questions on this here? This is. So, do we need to see another example of one of these? Yeah. Okay. Just wait. Just wait. In behavior of polynomial function. When we look at the graph of every single polynomial function, there's only one of 4 things it's going to do as we increase x to positive infinity and negative infinity. So a really big positive number and a really big negative number. There's only one of 4 things that it's going to do. Either the graph is going to essentially, the y values are going to go up both ways. They're both going to go to positive infinity. They're both going to go to negative infinity. Or one's going to go to positive infinity and the other is going to go to negative infinity. or vice versa. It's going to do one of these four eventually. Now, if you look at these four graphs, how it has a little dotted line in the middle, and then it becomes solid, because it's what it's saying is all the types that would fall into this stuff, where that dotted line is, it's going to change, it's going to do different things, it's going to operate differently. But at a certain point, it's going to start doing this. So we have four types. I'm going to get a highlighter out, if it'll let me. First thing I want to draw your attention to is this here. Degree is odd or even. So that's the first thing we're going to look at is the degree. If the degree is odd or the degree is even. Now, if the degree is odd, and positive, this is going to happen. As f of x approaches negative infinity, as x approaches negative infinity. Odd, negative. And f of x approaches infinity as x approaches infinity. So odd and positive is going to do this here. Now odd and negative, the next one. It says f of x approaches infinity as x approaches negative infinity. And f of x approaches negative infinity as x approaches infinity. That's just what the chart says, doesn't it? Okay. Now we also have even and positive. Even and positive says f of x approaches infinity as x approaches, and f of x approaches negative infinity as x approaches infinity. Not negative infinity, it's just positive. Because these here are going to make a little more sense. You'll have some graphs to these here, the even. Because what we talked about, our quadratics were even, yes? Every single graph of the quadratic function, either both sides went up or both sides went down, yes? And that's what it's saying. If the degree is even and positive, eventually both sides are going to go straight up. And we've seen that. Now, if the degree is even and the leading coefficient is negative, that's going to go down. So f of x will approach negative infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. So we have one of these four, okay? But it's all based on what is the degree and leading coefficient. Okay, so this is, let's just look at some problems. Let's look at this here. We want to describe the in behavior. Now, what is the degree? What is the degree of this function? Is that even or odd? Even. So the degree for this is even. The leading coefficient, is it positive or negative? Okay, so let's look at that chart. We have that chart right there on that page. Which one of those has an even degree and negative? The second from the top. And it says what? F of x, arrow, negative infinity as x, arrow, negative infinity. Yes? Because that's what it said. Then it says what? F of x, arrow, negative infinity as x, arrow, infinity. Yes? That's it. That's your answer. That's it. That's all we have to do for this here. Huh? No, that's it. That's literally it. We're done with that problem. Because this here doesn't seem too helpful, but it actually is. This is actually quite helpful. Because if we look at a function, especially our quadratics, from here, the ones that we saw, we had some that didn't cross the x-axis, it went straight up, yes? Well, since I know the degree is even, and some of them were positive, they were going straight up, f of x for positive is going to go to infinity. The function is going to go to infinity. Both sides, it's going to go straight up. That's what it's saying, yes? So will I ever have to worry about that coming back down? Well, no. This helps me determine what the function will do, what it's going to look like. Because if, for this one here, I see a function that's going down like this here, I know the function's going to go to what? Negative infinity. It's going to go to a super small number. The y values will go to super small numbers, or kind of really big negative numbers. I know that this side's not going to randomly decide to come back up. Because if I know it's going down, it's going to go down. It kind of gives us an idea of what the function's going to do. So let's look at this one here. What is the degree? Odd, because its highest exponent is 3. The degree is the leading coefficient. Negative, because it's negative 0.3. Yes? So I look at my chart. I'm looking for odd negative. An odd negative tells me f of x approaches infinity as x approaches negative infinity. And f of x approaches negative infinity as x approaches positive infinity. And that's it. It's saying what's going to happen eventually as the function, the value of x that we plug in, get bigger and smaller, go away from the origin. What's going to happen eventually to this function? And it's going to follow these patterns here. Questions on this here? We're ready for the next one. Describe the end behavior of this graph. So I need the degree. The degree is what? 3, so it's odd. Leading coefficient is positive. It's 0.25, positive 0.25. So I look at my chart and see odd and positive. So odd and positive would tell me that f of x approaches negative infinity as x approaches, and f of x approaches positive infinity as x approaches and that's all we have to do for these here. That is it. Any questions on any of this here? Was this as bad as y'all thought this was going to be? Was any of this as bad as you thought this was going to be? No. And that's all we're doing for today. So we're done. And this is the start of chapter 4.1.